This video is intended as an introduction to the video 4. There, you will deduce the general solution for the 1D collisions. As usual, we begin with the equations for the conservation of momentum and, for the conservation of kinetic energy. In this video, we study the situation where the masses of the two bodies, A and B, are equal. Divide both equations by m, and the second equation by 1/2. Rearrange both equations in order to have differences in both members. In this second equation, we find, now, in both members, a difference of squares. Unfold them. Divide the second equation by the first equation. Rearrange these equations, in order to have the canonical form of a system of equations, to solve for the final velocities of the bodies, A and B. Solve the system of the two equations. Use the known algorithm. We see that two bodies, with equal masses, during a perfect elastic collision, exchange their velocities. The so-called Newton cradle demonstrates what we found. Note that, in the shown device, there are 4 collisions in a row. See, now, several simulations of perfectly elastic collisions. Note how the bodies, with same mass, exchange their velocities.
Let's look at the coefficient of restitution, E, in the situation of a perfectly elastic collision of two bodies with the same mass. As we saw, bodies exchange their velocities. We take the approaching velocity as the difference, initial velocity of body A minus the initial velocity of body B. If we took the separation velocity as the difference between the final velocities, by the same order of bodies, we would get a negative value. The quotient for E would be negative. As it relates to energy, kinetic energy, that would not make sense. So, we will take the separation velocity by inverting the order of the bodies we took, while calculating the approaching velocity. It doesn't matter, one way or the other. Let's derive formulas for the final velocities of bodies A and B when the coefficient of restitution is not equal to 1. Equal masses, for now. We have a system of two equations. Note that the equation related to the kinetic energy is, now, the definition of the coefficient of restitution itself. Divide first equation by m, Remove the fraction. We have a system of two equations. Note that the equation related to the kinetic energy is, now, the definition of the coefficient of restitution itself. Organize properly the two equations and the immediate solution of the system will follow. Note that it is much easier to use the equation for the coefficient of restitution than the equation for the conservation of the kinetic energy, which has squares in it.
See, now, several simulations of inelastic collisions. Note how the separation velocity is in accordance with the value of the coefficient of restitution.
Please, solve this simple problem. Just place the numeric values in the formulas. Notice that, in the inelastic situation, E less than 1, final velocities are, also, let's say, exchanged, but paying a price. The deduced equations work for any value of E, 0 included. If E equals 0, bodies A and B share the same final velocity. Please, solve this simple problem. Just place the numeric values in the formulas.
See, now, simulations of perfectly inelastic collisions. See you in the next video. Collisions, one-dimensional, different masses.